Hi everyone, this is just a demonstration of the code that I've got running in MATLAB. So this is an implementation of the MapMapper algorithm, so you can load in. These are just a few example data sets, so let's start with pronged. So this is the sort of data set that Mapper is really suitable for analyzing, where you've got flares in the structure of your data when you're plotting it like this. So what we're going to do is, you can see here, you can select your filters, and this is the axis that we're going to filter along. So I think this is the horizontal axis that we're filtering along. And so you can set the resolution of your filter here, or the amount that each of these buckets is overlapping. When you're setting the resolution, or just selecting this filter, this is a histogram of the distribution of the points within the data set when you treat it as a point cloud. This data and this information is exactly the same as what's being displayed here. This is just a table, whereas this is plotting it. So obviously, once we've selected a filter, we also want a suitable clustering algorithm, and so here we can use both column 1 and column 2 to figure out how we should be clustering things together, and we'll just use a hierarchical clustering algorithm here. So if we click on Do Mapper, it'll just load that pretty much instantly. And yeah, you can see that it's slicing horizontally. The way that I'm laying this out is using the geometric mean of the points in the original way that it's being represented up here. Something nice about this code is that you can select particular nodes in one representation and see the highlighted points that are contributing to that node. And so this, combined with the fact that points in one corresponding with points in the other, means that you can pretty effectively visualize, oh, okay, this point is contributing to these components in the other representation. Of course, there isn't actually any intrinsic geometric information in the mapper output, so rather than using geometric mean, we can use a force-directed layout. And here we can sort of see, okay, that flare is no longer corresponding geometrically, because that information isn't really retained. It's just a element of the way that we're visualizing it. If you wanted to do a filtration along column 2 instead, which is the vertical axis, you can just do that. And then you can see we're slicing up and down the vertical axis, which is to say the slices are horizontal, but you understand for the visualization, hopefully. And yeah, so being able to visualize like this, you can see here, because we've got an overlap of 50%, that means that any point which isn't one of the outliers is going to be contributing to 2 buckets at any time. But if we reduce that overlap down, we should have some points which are, only contributing to one particular bucket. And what that's corresponding to is, you can sort of see that there are some points now which aren't in the overlapping components as we're moving along. So yeah, there's some other example data set, so you can open up an annular data set and see what happens if we apply mapper to it. So you can see the separated connected components. If we go into a force-directed representation, again, the fact that they're connected, we don't really have the knowledge that one of these is geometrically inside of the other, or we're really retaining as the topological information. If we want to, we can control-click to select multiple filters simultaneously. So rather than just filtering along one axis here, we're now filtering along 2. And if we then do mapper again, you can sort of see this representation now has substantially more nodes contributing to it. And then you can see it's not just 2 now. We have some points which are contributing to 4 buckets in the mapper output. When we do this as force-directed again, we don't really have a retained sense of one of these being inside of the other, because that inside of is a geometric conception about the way that we're representing things. I'll pull out the spiral data set, so I'll do this with the geometric mean again. You can sort of see it's got some stuff here. I'll actually bump that resolution up a little bit, so you can see these are connected components as we're slicing along. I will actually do mapper at this scale. That looks good. And then I'm going to scale the node size according to how many points are in it. And so since we're slicing vertically, it sort of makes sense that these are the nodes which are going to have the most points contributing to them. And then if, rather than representing this in a geometric representation, we've got force directed, you can see something like that. So that's really nice and convenient for when you're doing analysis on these things. So something which I've not yet covered is you can actually add custom filters. So in this data set, it's sort of represented as a few different Gaussian distributions. So rather than just filtering along column 1 and column 2, we can select both of those and then output the density. So if we want, we can just click add outputs as filters, and that'll add it there. Or you can go add selected to formula, and that'll add it as a component of this custom filter, which we can call, test density or something like that. And then if we go add filter, it will perform its calculations. And now, if we close this, you can see we've got column 1, column 2, and test density. So when we plot these, you've got column 1 and column 2, and then if we select that one, we've got the third axis of test density. You can sort of see we've got those peaks corresponding to where the information, where the point clouds are the most dense. So if we just drop back down to column 1 and column 2, and we're actually going to filter along the density axis. So this isn't a representation which this isn't a filtering axis in the original representation of the data. So if we just select a cutoff of 1, which is a bit larger, then if we do mapper, and here we kind of want it to be force directed. So I'll just reset this view, and then hopefully, yeah. So if we're not scaling the node size, you can sort of see these are components which are in the less dense regions, and they're not really connected to anything else. But then we have this branching structure, which you can see gets towards that dense component, or that dense component, or that dense component. And then these are less important. So if we're scaling according to the node size, you can see just visually when we're observing this, there's not that many points contributing to this. So the potentially really interesting stuff is happening when we're going along here. And if we bump up the resolution, we'll probably see a lot more disconnected components. And yeah, you can sort of see there's all of these disconnected components, but then also loads of weird connectivity structure that we're seeing down here on the outskirts. But then, yeah, being able to follow, okay, this is a dense component, this is a dense component, this is a dense component, and seeing where, like, this is sort of contributing to both dense components. So yeah, that's I missed anything? No, that's the sort of stuff which you can do with this tool. And so you can see here, this is just another way to visualize everything. With this particular example, it's sort of illustrating that here, this graph representation is representing up here where we've got 5 flares, but just because we're slicing vertically or going horizontally with our slicing, that flare is just being represented as a single node. Whereas if we select column 2 to filter along instead, we've got these 5 different branching bits. Or we can filter along both simultaneously. So yeah, this is maybe not necessarily going to be super useful for analyzing enormous data sets, though it's certainly a step in that direction. Technologies like IASD and their sort of suite of analysis tools is really useful. But maybe for a visualization setting where you're just trying to communicate to someone in an interactive way, the reasons that we might want to use the mapper algorithm for topological or any kind of data analysis, this could be potentially really useful. So the code for this is going to be up on GitHub. It'll be linked in the description, and hopefully you will find it useful. Right. Thanks very much.